Okay, now you guys are up. Thanks.
Okay, so our names are Joe, Nathan, Danielle, Riley, Jack, and Inga, and now we will be going into our presentation. So here we have the design overview. We have our full design here on the left, and then the 4 subsystems that we broke it down into. So we have the external housing, the motion, the internal housing, and the nozzle housing. And then we have to the right, the 4 photos that show what parts are included in each subsystem, and they'll be shown in further detail now in the future slides. And then we have our cost overview. So these were the costs that we calculated, and this was to ensure that we met with the customer need of not exceeding $100 for the bill of materials. So we have our material cost that came out to $78.98. We have the assembly cost that came out to $6.23, and the manufacturing cost that came out to $8.03. So how we got the assembly cost was we did use the approximation that we got from the Boothroyd and Dewhurst method. And that came out to the full assembly being 6 minutes and 59 seconds. But this was including soldering time and placing the inserts in the housing. So we were actually able to assemble it without soldering and the inserts already placed in under 5 minutes and only using 2 tools, because we did make an effort to standardize all the screws to help with assembly time. So it was under 5 minutes without the soldering and the inserts. And that's it for the cost.
Design and ideas way into our final. This illustrates the importance of conception in the design process. The source of proof of concept in original design generations.
Jack, your audio is chaotic. Is there somebody else that can hop in?
Yeah,
my Wi-Fi is cutting in and out a little bit. Can you guys hear me?
Yeah, we can hear you now.
Much better.
Okay, I don't know where I got cut off, so I'll just restart from the top.
And can I suggest just if you cut off your video, that often will improve the stability.
Okay, we'll try that. Design generations from day one show that even some of our initial thoughts and ideas were incorporated in some way into our final design. This demonstrates the importance of concept generation in a design process, as it gives a jumpstart to prototyping and gave our design a solid foundation to get off the ground with. From there, we moved into 3D printing prototype designs as a source of proof of concept to the original design generation. During this step, we would make changes to our size and method of tip ejection to something that is identifiable on the final design today. After plastic-based prototypes gave us a proof of concept, we began machining parts and assembling a working model that would reveal what small tweaks would have left to fix to get us to our final design. As these pictures show, our design process led us to make external housing longer to account for our volume requirement. This design change came in response for our inner nozzle size, which we wanted to be as long as possible so that it would have a smaller microliter per step. Next, the exterior housing adds a stabilizer for the ejector arm, which each prototype would make thicker for better support of the ejector. After our prototypes showed a proof of concept for our design, we went and made them look sleeker with rounded corners, the walls are made thinner, and the tool connection port was moved to better balance the center of gravity. The stabilizer was consolidated due to the internal housing being changed from the addition of the removable nozzle. For the final design, the top was modified to have a top plate that clicks into place to save time on assembly and give quick access to the location of the plunger and motor coupler. Finally, ventilation was added to the top for the motor heat. The ejector arm had many iterations, but that was mostly for the purpose of fine-tuning the design. The only major changes made were to round the connecting surface at the top to better interface with the housing and final design, and to change the kicker to a semicircle to better distribute the force so that the arm can apply to the pipette tip and prevent jamming found during previous testing. The internal housing structure changed at first to allow for limit switches and an interchangeable nozzle. The red design decreased the number of switches used as we determined the top limit could be determined through a controller instead of a sensor. From there, we addressed the fact that since we are gluing the nozzle in place, the holding mechanism should be removable for maintenance on the O-ring. The switch was put horizontal for a more consistent catch of the motor coupler, and the final design accommodates the triangular nozzle housing insert that was made to reduce the necessary screws and to allow for easier assembly along with the oval leg base, decrease the total size of the design.
My name is Joe Jarzynski, and I'm going to continue talking about our design's progression. Our initial design's plunger was 3D printed and combined with the motor coupler. We quickly found out that this wouldn't hold a seal because of the discrepancies in the 3D printed dimensions. So we made it out of aluminum and had 2 O-rings attached to the plunger. This worked better, but it still had slight leaks at the tip of the pipette. So we changed the location of the O-ring to the inside of the nozzle. The final design was the same, but it was made from stainless steel in order to match the stainless steel of the nozzle's final design. The coupler design stayed consistent throughout with small changes to affect ease of assembly. The small tab on the later designs was implemented to help with the ejector system, and the final design had an increased thickness and less holes to reduce stress and time of assembly. Next slide, please. The first design's nozzle was printed on the outer housing, but we realized it did not create enough seal for the pipette tips. Then we tried a machine nozzle with a tapered end and an O-ring on the plunger, which was still not completely sealed. Because of this, we added an O-ring to the inside of the nozzle, which worked perfectly in maintaining the steel and not spilling any fluids. The final nozzle is the same design as before, but made of stainless steel to avoid corrosion with the plunger. After the O-ring was implemented to the nozzle housing was created to ease access to the nozzle for replacement of the O-ring. The housing worked once it was implemented, but was changed to reduce material and decrease assembly time and parts used.
In terms of failure analysis, starting with the nozzle, deriving the motor force from the motor holding torque, it applies a maximum force assuming it applies the maximum force, which is about 100 newtons. The resulting hoop stress for a thick-walled pressure vessel is 2.5 megapascals. This assumes the tip is clogged and the chamber is pressurizing, assuming a worst-case scenario. The resulting factor of safety is 86. To attach our nozzle to the nozzle insert that Joe previously talked about, we use cyanoacrylate, which when fully cured has an adhesive strength on the plastic of 7 megapascals. Assuming the adhesive is spread evenly along the insert's walls, the resulting force is 29 kilonewtons. Because our motor at most can output 100 newtons, the factor of safety is about 300. The threaded insert analysis was limited by the testing equipment we had on hand. When trying to pull the insert out, the force gauge maxed out at about 45 kilograms of force. Distributing that across the insert, the resulting factor of safety is within the range of our equipment is 2.22. But it's likely much greater due to the limits of our experimental data. These tests were also done at room temperature. So assuming the plastic deteriorates in any way at different temperatures, it'd be different. An analysis was done for the crucial plastic parts. Starting with the ejector arm, we derived the spring constant in order to develop the force that the spring would apply. Using that, we calculated the force from the tip and used that to determine the bending stress at that force and location. The resulting factor of safety is 1.33, which is the lowest one that we were able to find. The motor coupler bending stress was determined by assuming the resistive force was applied to a cantilever beam, assuming the motor is no longer moving and that the lead screw is stuck in place. The resulting factor of safety is 1.77. Next slide. As for fluid analysis, while running the test, we timed how long it would take to dispense the water to observe the flow rate. Given the flow rate at each volume, the line of best fit from that analysis, and the diameter of the pipette tip, the fluid's velocity was determined. And relating that velocity to the Reynolds number equation, we get a graph that grows as the volume increases. For our volume range, the Reynolds number all exists below the 2400 threshold for laminar flow. Because the flow is laminar and not turbulent, the flow does not aerosolize as it dispenses. Next slide.
So one of the tests or calculations we needed to do in order to do our testing was determine the volumes per step that the motor would be able to hit as we're doing our testing. And so to find this, we looked at some of the motor specs that was given from the manufacturer. And so some of the things that we found were it has 200 steps per revolution, and it had a thread pitch of 2 millimeters. However, the lead screw had 4 starts. So in actuality, the one rotation was equal to 8 millimeters. And so converting some of the units, we were able to find that 25 steps was equal to 1 millimeter, or 1 millimeter was, or one step was 0.04 millimeters, which that was what we used in our next calculation down there at the bottom, the theoretical volume displaced. And in order to calculate this, we did the volume or displacement equals the pi d squared over 4 times h, where d is a diameter of our plunger, which is 9.53 millimeters, and h was the millimeters for one step, which is 0.04. And when we calculate that out, we got 2.85 millimeters cubed per step, which is also equal to 2.85. And so that was, on the next slide here, one of the inputs that we used for our testing. In total, throughout the whole past month or so, we did around 300 tests. And in order to get it fully working, we did 2 calibrations. Each were 60 tests each. And so some of the inputs that we used within the code, so we had our desired volume, so the user would input a volume, and then previously we just calculated the microliters per step, so that was 2.85. And then the initial testing we did was using 1.8 degrees per step, which was just a specification from the motor. And our procedure for doing these tests were, we had our volume range, which is 500 to 5,000. And so plus or minus 10 microliters. So we wanted to make sure that we can hit that consistently. And so in order to do that, we tested that volume range at increments of 500 microliters, doing 6 tests at each volume range. And once we collected our volume, we put it on a scale, a high precision scale, and measured the mass of it, which the scale was capable of hitting 0.1 micrograms for the testing. So pretty precise. And then so our initial calibration, which you can see on the left, that was done with the initial testing. And so pretty much how we did this was we took a look at the desired versus the actual. So we're plotting the volume in microliters versus the revolutions that the motor is rotating in degrees. And so we took a look at where we are actually versus where we need to be, and simply adjusted by the degrees to hit the actual volume that we want. But once we implemented that into our code, we noticed that we were still off a decent amount. And this could have been due to, some manufacturing issues, or, the lead screw had a bit of play for the coupler. So that could have added some of the error as well. The trend line that we fitted initially also might have been like a piecewise function. And so it could have had a different slope at the bottom of the volume range versus the top. But anyway, the way that we calibrated it at the second time was we took a look at the average error in degrees that our motor needed to rotate in order to get to the desired volume. And we took a look at each volume range, so 500, 1,000, 2,000, and we implemented this second order equation into our code in order to adjust by that degree value. And so once we implemented both of these calibrations, we're able to hit our accuracy and precision for each volume range, and we proved that through our testing and through our final demonstration this past week.
An accuracy of plus or minus 10 microliters for our volume range was met with 0 backlash or aerosols. Our total cost came to $93.29, which meets the requirement for a cost under $100. The manual assembly time is under 5 minutes, given that the time to solder and place the threaded inserts in is not included. Although we were unable to have a toolless assembly and disassembly, the majority of the fasteners were standardized, which made for easier assembly. As for the 384 weld plates in 6.5 minutes, this requires processing 0.985 well plates per second while including filling up the pipette multiple times. And we found this need to be unobtainable. Our design has a lifetime of at least 10 years and is capable of operating for 2 weeks without intervention. And our group thanks you for your time, and we will now be open to any questions.
Okay, so I think Dr. Nemi indicated that he's got a visitor in his office, so asked me if I could just facilitate the Q&A period. So we want to first thank this group for sharing your presentation and your design with us. Excellent work. I especially like the testing charts and the curve fits that you guys did. I actually have a question which probably isn't relevant to anything, but you mentioned in your the 3D printing and the fabrication of your housing that you sort of clip the corners to make it I don't remember the word that you used, but it was like stealthy or streamlined or something like that. Was there any, I guess, engineering benefit to doing that, or was it just aesthetic?
Well, it made the design sleeker.
Sleeker, that was the word.
Yeah, it decreased the area of the whole design as well. So it made the design smaller as it like cut the corners off, giving it like more, taking up less room essentially.
Okay.
We also decreased the thickness of the walls, so that's kind of how you see the like the attachment, the mounting plates kind of have like a part sticking out. That was due to the decreased wall thickness.
Gotcha. So did it result in faster print time as well? Like would you characterize making it sleeker as like a positive move in terms of design for 3D printing?
I would say so, yeah. Yeah, it did decrease the print time.
Great. Yeah, we noticed that in the beginning. It wasn't just you guys, it was like every group was like printing out these big sort of clunky enclosures. It was like, boy, we need to figure out a way to speed that up. So yeah, I figured by cutting down the total amount of volume that you need to print, you would also speed up your print time, which is great for iterations, right? The faster you print, the more you can iterate. So okay, just curious about that. Are there any questions from our panelists?
Yeah, guys, this is Tom Singer from Northrop Grumman. The little kicker that you're using to pop off the pipette, I appreciate you did a stress analysis there. I'm not sure you're really capturing the full effect. The corner there is going to act as a stressorizer, and I don't see that you've accounted for that in any way here.
So in our design, we did put a fillet on that corner so that we don't have a stress concentration. This image here might not be the most up-to-date one, but in our final design, there is a fillet so that there's not a sharp corner.
Yeah, I mean, it certainly helps. I would hesitate to say that there's not a stress concentration there. A fillet is going to reduce relative to a sharp corner, but it's not going to be zero, or well, I guess it's a factor, so it's not going to be one. The bigger you can make that fillet, the better. It strikes me as and you show it yourself, right? You're saying you have the smallest factor of safety on that bit. It strikes me as the flimsiest part of what otherwise seems like it's a fairly robust design. And I wonder if maybe you could bulk that up a little bit. I would also ask what the factor of safety requirement is for your customer, and if that's going to meet it. And again, when you start considering a stress concentrator from that fillet, what that does to your actual factor of safety.
So a larger fillet there also manipulates the bottom plate for our inner housing, which we can obviously do. That was one of our design kind of constraints, was that the interaction between that fillet and that design housing. Because the larger that fillet is, the lower it rests against it. And so the pipette will not fit quite as far up the nozzle, I should say.
There's definitely some things we could do to increase that factor of safety, increasing the thickness of it, changing the way that it fits into the housing. We could kind of have it be inset rather than, at the very bottom. So that would give us a lot more room in terms of adding thickness, and adding a bigger fillet as well. But I don't think, at least from what I remember, I don't think there was ever a customer requirement in terms of factor of safety. So that would definitely be something to follow up with the professor or the customer on.
Yeah, I would suggest that. I would also suggest looking at the thermal effects on the plastic. Right? I mean, you're inside a chamber that's getting up to, I think I remember, like 70 degrees C or something like that, and humid, and both the temperature and potentially like moisture uptake are going to affect the strength of your material.
So I believe the transition temperature for the PET G is about 80 degrees Celsius. And so in accounting for that, we made this part pretty much as bare bones simple as we could. And so that the ability for reprinting it or just manufacturing multiple of them is pennies on the dollar, so that like it would be easy to replace when the need arises.
Yeah, I mean the problem is when the need arises, you've already like botched an experiment, right? And that's potentially problematic, because you're not ejecting a tip, and then you don't necessarily know that you haven't ejected a tip, and then you go try to load a new tip, and the whole thing crashes, and the experiment grinds to a halt. Yeah, that I would really hesitate to have a point of failure like that, and if you do, I think it needs to be analyzed significantly more thoroughly. Let's see. One other thing I have here, and I'll echo that you've got customer needs in here, and that's great to see. I appreciate you tying your design back to that. The accuracy need. I wonder if you could speak to the impact of wear in your system, how that will affect calibration.
Yeah, so that's not necessarily something that I considered. It's a good point. I appreciate the question. I guess one thing that we could potentially do in terms of a calibration, I think it's reasonable to say, every so on, every so amount of period, in terms of time, you could maybe do some calibration just to ensure that it's running properly. For example, the scale that we were using, there was a calibration that you're able to do with like a known weight, and so maybe we could incorporate something similar to that with like a something in the software, like you start a calibration command and it goes through some process of calibrating. The 3D printers also do something similar as well. So that's not necessarily something I considered previously, but yeah, that's a valid point if we're going to be operating for 10 years.
Okay. We're right at 1 o'clock, but we did start a little bit late. So I want to give time for maybe one more question if there are others from the panel that want to ask them.
I'll go my one more.
That's fine.
You've got a lot of 3D printed parts here, and in other groups I've asked, what's the intent? Is this a one-off design, or is this something that's intended to be, produced and manufactured on a scale of hundreds or thousands? And I wonder what your thoughts on that are, and how that relates to something that has a large percentage of 3D printed parts versus something that might scale a little better.
Yeah, I would say so. I think right now we're primarily just doing the project for our customer in one of the UF research laboratories. However, I would say once this design is finalized and everything is working as it should, I don't see why we wouldn't commercialize this device and sell it on the market. In which case, if we're doing mass production, 3D printing would definitely not be the best route in terms of producing this design, we'd most likely go something with like injection molding. And that also help our design as well for just having a more rigid plastic components. You know, like for example, I was doing a lot of testing with snap fits earlier. And one of the things that I noticed was a lot of the snaps were snapping across the layers. So I had to, you know, adjust the print orientation to account for that. And, you know, but with something like injection molding, that wouldn't necessarily be an issue. So in terms of, you know, having a more robust design and, you know, being able to mass manufacture that would definitely be the way.
Do you see any impacts to the basic concept of your device with different manufacturing techniques?
It shouldn't, no.
I would say though that we did optimize some of the aspects of the design for 3D printing purposes. And so some of the adjustments that we made were designed so that there would be less support when printing and then higher accuracy due to less removal. So there might be some changes here and there that might need to be made for conventional printing or conventional manufacturing.
Okay.
Okay, so let's wrap it up there because we're a few minutes over. I want to make sure everybody gets a little break before we jump into the next session. So once again, I want to just express my appreciation for you guys giving your presentation in this first cohort. We had a couple of bugs that forced us to run a little behind and change Zoom links and everything at the last minute. So appreciate your flexibility with that. And I'll use the same word that Dr. Nemi used when he was talking to the previous group. So you guys are free in air quotes, which is not really true because you still have to do a final final report. But anyway, congratulations on at least wrapping up this part of it. And we look forward to seeing the final manuscript that you guys come up with.
Awesome. Thank you, Dr. Traum and Dr. Nemi, for all of your teachings.
Thank
and
you.
Our sponsors as well. Appreciate it.
Yes, thank you.
Thank you.
All right. Have a good week.
You as well.
All right. Let me stop recording.